Before we move out of proof by contrapositive, I do want to talk a little bit about something called biconditional statements. So first, we're going to define what a biconditional statement is. It's basically a statement that says if and only if. We're going to show that proving a biconditional statement is logically equivalent to proving two conditional statements, which sounds bad because we're going to be proving two different statements, but it is good in that we are proving conditional statements, which we already have a nice model for. And then we're going to do an example to show how it works. So a biconditional statement is a statement of the form P if and only if Q, where P and Q are statements. So in symbols, it's P with a double arrow Q, which you may have seen when you were doing truth tables back in Math 225. The statement is true when both P and Q both have the same truth value. So either they're both true or they're both false. So here's what the truth table looks like. You can see at the top where P and Q are both true, our biconditional is true. At the bottom where they're both false, our biconditional is also true, right? They just have to have the same truth value. And in the middle where P and Q have different truth values, the biconditional is false. Now, it's very difficult to prove biconditional statements directly. There are some very rare circumstances where that is not true, but almost all the time, proving them directly is very difficult. So we use an equivalent form, which is P if and only if Q is equivalent to if P then Q and if Q then P. And if you want to see why this is true, here's what the truth table looks like for if P then Q and if Q then P. P implies Q is true precisely when P is true and Q is false. So you can see in that third column you have T, F, T, T. That's why that is true. Q implies P. That is going to be false is precisely when Q is true and P is false. That's going to be in the third row. The only time that both P implies Q and Q implies P are true are in that top row and bottom row. And that's why you have the T on the top, or T on the bottom. And in the other two situations, one of those is true and one is false, so you get false. Right? And if you look carefully at it, it's exactly the same truth table we had for P if and only if Q. All right, so thus, if we want to prove a biconditional, then we have to prove the statements if P then Q and the statement if Q then P. So that means we have to have two proofs for proving one biconditional statement. All right, so here's an example. Let n be an integer. We have n is even if and only if n plus 3 is odd. So first thing we're going to do for our reader is let them know that we're not going to prove it directly. We're going to use an equivalent statement. So to prove this theorem, we must prove both if n is even, then n plus 3 is odd, and if n plus 3 is odd, then n is even. So we begin by assuming n is even, this is from the first statement, and showing n plus 3 is odd. Since n is even, we have n equals 2k for some integer k. Then n plus 3 is going to be 2k plus 3. If we do a little bit of algebra magic, we get 2 times k plus 1 plus 1. And since k plus 1 is an integer, k is an integer and 1 is an integer, it follows that n plus 3 is odd by the definition of odd integer. Now we have to prove the other part of the theorem, which is that we assume n plus 3 is odd, and then we show that n is even. Since n plus 3 is odd, we have n plus 3 equals 2k plus 1 for some k and z. That's just the definition of odd number. And again, we're going to do some algebra magic. So if we want to look at what n is, that is going to be n plus 3 minus 3. That gets n plus 3 involved. N plus 3 we already showed is 2k plus 1. We can substitute that in. Then if we simplify, we get 2k minus 2. We can factor out the 2 to get 2 times k minus 1. Now k minus 1 is an integer, and by the definition of even numbers, that tells us that n is even. So now go ahead and work on the activities for biconditional statements. That is going to be on the PDF file included with this video.